In the last video what we were actually talking about was a crossbar as a packet switch, and I have actually talked and told you in the end that there will be interface boards at the input ports as well as at the output ports. Okay. And all packets at the interface input interface boards will be analyzed for their header, and this information will be passed on to the controller, and this controller will essentially will now be regulating the crossbar at every time slot, and as a result the packets will be now moved on to the outgoing ports, and then they will be transmitted further to other switches or the users whoever will be connected. Okay. So, in this case the way actually I have assumed was that this crossbar which is being used to do the switching is operating at the same speed as the input line or the output ports or output lines. Okay. So, one slot takes one packet here, so it actually takes exactly one slot to transmit the packet all the way to the output port. Okay. So, internal speed of this is same as the line speed. So, that was the assumption. So, but switches actually can operate in slightly different fashion. I can actually build up, if I should actually show the interface boards here. What I can do is, if I actually provide these input and output interface boards, so my line rate is different, is going to be same, but from this interface input interface board to the output interface board and this switch, I actually can transmit at higher rates. It need not be the same rate. Of course, certainly it cannot be smaller, it has to be either equal to the line rates. So, line rates what are being prevalent here, I call this line. So, I can actually operate at higher speeds. So, suppose if I operate at double the speed, then what is going to happen? So, if it is operating at double the speed, in that case in this slot period, the slot period here inside the switch will be of a half duration, half of this particular slot period which is there at the input or at the output lines. Internally this will be 2 slots. So, this technically means if I actually I can transmit in this one slot, I can transmit 2 packets to the same output. So, that should be feasible. Okay. So, I define this particular rate, the factor, this is a k times the line rate. So, I call it the speed up factor. Okay. So, this speed up factor, if it is 2, two mini slots will actually be used within the same period for transferring the packets from the input interfaces to the outgoing interfaces, which actually means in one slot period this crossbar can be configured 2 times. Okay. So, the simplest case is when k is equal to 1, which was the original case. So, we will now be talking about when k is equal to 1, when k is equal to n. So, where n is the number of ports here, n by n switch, and k can be something which is greater than 1 and less than n. So, there are 3 cases. So, let us see when k is equal to 1 what is going to happen. So, we will define something called head of the line blocking for this particular case. So, head of the line blocking will happen in this case and can also happen in this case. It will never be happening for k is equal to n. So, when you have this case, technically the interface board will be like a queue, it will be storing the packets. So, I am showing 4 of them, there are 4 lines, and the packets which are there in the front, their headers have been now communicated to the controller, and this controller will now configure the crossbar As a result, the packets from here will now be switched out to the outgoing ports. Now there are possibility, for example, when this is going to happen is when each one of them want to go to a different outgoing ports. Okay. But there is a possibility that these packets which are there in the front may have, some of them, maybe 2 of them, maybe 3 of them would like to go to the same outgoing port. Then what is going to happen? Okay. So in this case, for example, these are 2 packets or 3 packets which want to go to the outgoing port number 1. So when these headers will be analyzed by this switch, by this controller, it will configure the switch, but it also has to decide that all these 3 now cannot be pushed to the outgoing line at the same time. So 2 of them have to be stopped. These 2 interface boards have to be told that do not transmit. Only one of them will be permitted to transmit. So there is going to be a feedback which has to go to now these control boards also. So they will be essentially now throttled or regulated by the controller. So as well as the switch will be configured, and these header information also should need to come back to the controller. So controller has to do the computation, and based on that it will decide what is going to be the next state of the switch and what should be the it will give a command to the interface board whether a transmission should happen or should not happen. Okay. Now in this scenario, when 3 packets which are at the front, which are supposed to be transmitted in the current slot, want to go to output 1, only one of them will be going out. So, but there may be possibility I might be having 2 and 3 here, this might be a 4. So 4 goes to 4. There was no conflict for 2 and 3. I could have transmitted 2 and 3 out to the port number 2 and 3, but I could not do so. Because I am actually taking first come first serve policy, there is only one single queue at the input. Okay. So then there is no transmission here, there is no transmission here, there will be transmission here, there will be a transmission here. Packets will go out, so that this particular packet will move further and this packet will be erased. So whatever was X will come here ultimately, whatever was Y will come in the front ultimately, this will remain as it is. 2 and 3 could not be transmitted. Now this is happening because of there was some what we call packet which is going to have a contention, and that packet was lying in the front of the queue, which has not allowed the packet which was not having contention in that slot, that packet could not be transmitted. So this kind of blocking is known as head of the line blocking. So we simply usually write as HOL blocking. Okay. So this is what was happening with k is equal to 1. Now interestingly, you can also observe the moment packet is transmitted, this transmission is happening at the same rate at which these lines are operating. So packet will come and they will be immediately transmitted out to the next switch or next user or next network, whatever it is. As a result, I need to buffer only packets at the input, there is no buffering at the output. Okay. So I need to essentially queue up or store the packets at the input, and these need to be stored because of this head of the line. If this does not happen, if we can guarantee in the transmission that all 4 packets which are coming, they will never ever be having a conflict, they will never be contending for the same port. In that case you only need one buffer, because whatever will be coming will be transmitted out, and next slot next packet will be coming and it will be transmitted out. But in real life that does not happen. We need to have a queue, and this queue can actually build up to a very large value. In fact, we will analyze that what is the maximum throughput which I can achieve in this kind of case because of this head of the line blocking. I cannot certainly operate at 100%. That can only happen if all the packets which are coming in the same time slot are not contending for a same output port. They are all being mapped to different outgoing ports. So there is a permutation kind of thing, routing which is happening there. but that we cannot guarantee. Now let us look at the second case, which is k is equal to n. What does it mean? That the switch these are the interface boards, I do require interface board in this case on the outgoing side. So this is switch is operating, this is the slot period here, this same slot period now is being divided into n sub slots. So you will receive one packet in this time period. In this same time period, the transmission from these interface boards, n packets can actually be transmitted, okay, and these can be received here, but then they will be again transmitting only one packet. So in a time slot when the packets will be arriving, so there is a queue here which gets formed, so I can actually draw a queue on the board. So even if all packets want to go to the same outgoing port, so since there are n possible slots, even if all n packets which are there at the head of the queue want to go to the same port, I can do so. I have to just say the controller will get all this information, it has to tell all of them back that they have to do it in these mini slots, they have to do the transmission. So all of them will be given a separate sub slot or separate mini slot, because this system is operating at much higher speed, at n times the speed. So all these packets can be transmitted and they will be received here, but you are receiving at a faster rate, you cannot transmit at that rate to the outgoing line. You have to transmit only one packet in this full slot, not n packets in a slot. So as a consequence, you do require a buffer or a queue here, so all these n packets can arrive, and then one by one you will keep on transmitting it out. But do you require a queue here? You actually do not require. In all the synchronized slots, one packet comes in, all of them will be pushed out, queuing will be happening only at the outgoing line, not at the input, when k will be equal to n, when speed of factor is n. So when speed of factor is 1, you will end up in an input queued system, and when k is equal to n, you will end up in a output queued system. There is no head of the line blocking in output queued system. Another important thing is the line rates are same, and so far your probability of arrival here is less than 1, and there is a uniform routing. So there is an equal probability that packets from port I will be going to any one of the ports on the output side. So these are equally likely happening. So because of this, this system will always remain stable. Okay, so whatever is the arrival rate and departure rate, they can at most be 1, and they will be same arrival and departure rate statistically. So this queue will always remain bounded, it will be always be finite and stable system. Okay. You can also have a case when k is not equal to n, so you can have this particular scenario. So in this scenario, what actually is happening is k is not n, k is not also 1. So far k number of packets which are contending, they will be, you will be able to push them out to the outgoing output buffer, but the moment you have k plus 1 contending packets for the same outgoing port, so k of them will be passed on to the buffer, and the remaining ones have to be still you have to hold them here in the input buffers. So you will be requiring in this scenario an input buffer as well as an output buffer. But normally the chances that all n, if n is for example 16 by 16 switch, all 16 packets at the input buffer would like to go to the same outgoing port, that chances will be very low, maybe 2 or 3 after that the probability will keep on falling down drastically. So even if you put k is equal to 2 or 3, the buffered requirements at the input can be drastically reduced. You only require the outgoing output buffer system. It will work as good as an output buffering system actually. So, and this technically is not an input queued, not an output, but this is a hybrid system. And very soon, even with very small values of k, this will be working as good as an output queued system. So let us come to the input queued system. In this case, there will be k packets which can be directed to the same outgoing port. So let me just clean it up. So it's no more an output queued system, I am considering an input queued. So you will have and out of this the k of them are being directed to the one single port. Okay. So there are k packets which are coming at any point of time, and remember here, sorry, this k is 1, I should actually, speed of factor is 1, but there is, let me call it L number of packets which are coming in. So these L packets, when they are coming in, only one of them will be actually routed to this side, and remaining L minus 1 has to be stored here. Okay. So every time when actually you are going to have this kind of contention, so next time there may be new packets coming in for the same port, you may be having L minus 1 backlog from the earlier transmission, earlier slot, and more new packets. Now which packet you should choose for sending it to the output? This is an important question because this leads to the performance improvement. So you can actually choose, have very simple strategies. You can actually say that there is no strategy, I am just going to pick up. So even if there is out of the L contending packets, some packets are there from even earlier slots which could not be transmitted earlier, but they are still hanging around. I will not give them a priority, I will just pick up anybody randomly out of this thing. This could be one strategy. So you can say one of the L packets randomly being transmitted. You can actually take packets from the longest queue. So the packet which have been backlogged for longest period of time, you are actually giving them a priority in this case. Technically, you can also have a strategy. You can define the priority actually of the various inputs, packet from the highest priority queue is taken. So you can actually define the priority among the input ports. So in fact, remember all these switches in real life, when we implement, we need to implement priority classes, okay, because quality, based on quality of service, I should give priority to certain packets and should give less priority to others, okay. So now the question which we need to ask, now coming back to, first of all let me analyze the output queued system, then we will come back to the input queued one. So these are basically the issues which are there. So for an output queued system, the question which we are going to ask is, so we have to define something called P, which is the probability of packet arrival. We do not use arrival rate like lambda and a Poisson statistics. Now everything is slotted. In a slot, either the packet will come or packet will not come. These are only two things which will happen. So probability of packet arrival in a slot will be P. So that is going to be our parameter with which we are going to look into the performance of the switch. Okay. So and we are also going to assume when a packet comes at the input, it can be with equal probability can be directed to any one of the outgoing ports. So, probability it is going to be directed to a port will be 1 by n. So, it is a basically uniform traffic condition, that is what we are assuming. Now, what we want is, as your P will increase, P will change, it is a parameter, then what is going to happen to the average Q length at the output Q. So, I am actually talking about a speed up factor of n. So, what happens to the average Q length and what happens to the average waiting time. Now, because of the contentions or the packets may be trying to go to the same outgoing port at the same time, packets have to now spend some time at the switch. So, when I am especially worried about how much delay it will take for a packet to reach from source to destination, this particular factor, the queuing delay, also need to be incorporated. Remember when I was talking about circuit switching and packet switching in the previous video, I had drawn the timing diagram. I have only given the header processing time. I have not actually included there the waiting time in the queue. So, waiting time in the queue should be very small, especially if it is a real time traffic. Otherwise, my round trip delay will become larger than what is required and I cannot transmit voice or video, live video streams over it, over the network. Let us define, let us start analyzing it. So, if these are n packets, each one of them will get a packet with probability p. With 1 by n probability, it can actually go to each one of the ports. So, with p by n, I can get a packet from here, with p by n, I can get a packet from here. With 1 minus p by n, I will not get a packet from this particular input port, and there are n ports. So, what is the probability that an output thing I will get? Now, remember this switch is operating at k is equal to n. This is an output queued switch, there is no input queue. So, what is the probability that I will get I packets in a slot? So, I define this as a parameter. So, we call it A, which is the number of packets arriving at a particular output. So, I have actually tagged an output, I am analyzing that, and whatever I am analyzing is going to be true for all other outputs also, okay, because I am not differentiating, they are all behaving in the same fashion. So, this we call it AI is probability that A will be equal to I. So, this will be given by, because there are n inputs, out of which I of the inputs will be having the packets directed to this particular switch, then only you can get I packets, and this can happen in NCI, n commutatorial I ways, n factorial by I factorial by n minus I factorial, and p by n is the probability that the packets I packets will be directed, and 1 minus p by n will be the probability that packets will not be directed. So, that will be the AI. So, once I have this probability distribution, so this is a discrete probability distribution where I can take values from 0 to n, I can actually find out the probability generating function of this. So, this will be given by Az, remember is nothing but the Z transform, that is the way it will be written, I goes from 0 to infinity or whatever are the valid values. So, in this case this will be summation of I goes from 0 to n z raised power I ai. Okay. So, we can actually put in the values of ai from here and then solve it. So, this z I actually I can take inside with p by n. This is a complete binomial. So, I can write this as 1 minus p by n plus z p by n raised power n. So, that should be the value of a z. And as n will become very large in limit when n goes to infinity, this will actually can be approximated as an exponential. So, it will be like when n goes to infinity, p goes to 0 such that n into p goes to some constant, we call it lambda. In that case, this a z will become e raised power minus so probability of ai, this one, this will get converted to, let me first of all ai will be converted to lambda raised power I e raised power minus lambda by I factorial. This get converted to the Poisson and once you solve it, you actually will get the similar procedure. So, you will get PGF, which is a of z will be summation of z I lambda I e raised power minus lambda by I factorial so this n will become infinite in this case, and you can actually write lambda z raised power I by I factorial e raised power minus lambda z. So, we will have this. So, we need to actually take this e raised power minus lambda out and e raised power plus lambda z out. So, this thing will turn out to be 1. So, which is the identity. So, ultimately your solution will be this, which will give you e raised power minus lambdas 1 minus z. So, that will be the probability generating function for an infinite dimensional switch, infinite size switch. So, now for such a case, for this one, this probability generating function a z is known to me. Now, we have to also understand that this q at time slot m minus 1, this was containing these many number of packets. When the m slot is going to happen, then the new arrivals which are going to come in m slot was actually am, and there was one packet which has gone out because it was transmitted out. So, which actually means q of m, the leftover packets will be nothing but qm minus 1 plus am minus 1, and of course, if this value cannot go negative. So, I have to now write down here that q of m is maximum of this or 0. Okay. So, when for example, this value is 1, there is no arrival, 1 goes out, it will become 0. When it is 0, there is no arrival, you cannot have a packet going out. So, that is why there is a maximum operator which has to be happening. So, it will be either this or this, whichever is maximum. So, this q will be defined by that. This am will have a probability generating function. The distribution of this, the PGF, will be given by this expression for infinite size switch, and for a finite size switch this is what will be the expression. So in fact we can even draw the Markov chain for this. So you can refer to any book on queuing theory, the standard textbook for this one. I am actually directly using the results. So you will have something like 0 state when there is no packet in the queue. So number of packets which can come, if there is only one packet which comes in, that packet will come at the output buffer and it will be going out, you will still remain in state 0. If there is no packet which arrives, then also this is going to happen. So A0 plus A1, so that is the probability of arrival of 0 packet or 1 packet. Okay. So from 0 you can transit to 1 state if you are going to have 2 packets arriving. You can do a transition to 2 if there are 3 packets coming in. Okay. Ultimately you can actually have n packets coming in. So you will might end up in n minus 1 state. Okay. So these are the multiple. Remember earlier Markov chains which we did was far simpler. Okay. So this one, similarly from 1 if I want to go to 2 I have to have A2 coming in, A3 I will come here, and from here if I want to go, so this will essentially will recurse in this fashion. Similarly this is what is going to happen, similarly for this. Okay. So this one will be happening is when there is no packet coming in, when there is no packet coming in, when there is no packet coming in, and so on. So this is what will be the Markov chain. So this of course you can write down the equations, balance equations and solve and get all the state probabilities. Okay. And once you have all the state probabilities you can actually use this to compute what is going to be my mean queue length. Okay. There is an alternative way also. So I can directly use an expression which is for this kind of queue. So if I actually take this direct result for a PGF for Q, so QZ is the PGF, QZ, the PGF of this kind of queuing system can actually be written in terms of AZ and an expression. So this will be given by this. And the beautiful thing about QZ or any probability generating function is that I can estimate any movement of the distribution using this. So first movement is the average value which we would like to actually know, that is what was the question with which we started. So if I know for example AZ, I want to find out the mean value. So this was given as summation of z raised to power I pi, I goes from 0 to infinity. If I take this derivative, then I will get I z raised to power I minus 1 p of I, and if I take z is equal to z limit goes to 1, in that case this will turn out to be and this is nothing but A bar, okay, the average value. So I can similarly find out what is going to be the average value for the Q. So if I find out Q bar, this will turn out to be n minus 1 by n. This again I am actually using a direct result because this is there in all standard text on queuing theory. So this will be given by p square divided by 2 1 minus p. Now interestingly, this is an expression for the average queue length of a MD1 infinity queue. So MD1 infinity queue, what does it mean? So this expression, the encircled one, is for this. Only thing which comes because of these batch arrivals. So the packets which are coming into the output queue are coming in batches, depending on how many are trying to contend in every slot. So because of that you get this thing. If there are no batch arrivals, okay, then it will become simply MD1 infinity queue. So when n actually becomes very large, this will cancel. N minus 1 by n will almost can be approximated as 1, and q bar, the queue will exactly behave as if it is a Markovian arrival, deterministic departure, single server and infinite buffer queue. What does it mean is that there is a queue, there is only one single server, so there is only one guy, okay. Every packet will take exactly same time, is a deterministic thing, okay, it is actually constant, is a constant departure process. Every packet takes exactly one slot time to go out, and the packets which are arriving, they are happening because in the Markovian process. So whatever is the average value, so number of packets arriving in time t will be given by lambda into t raised power n e raised power minus lambda t by n factorial. So this is the probability of n arrivals in time t. Now interestingly, when I am actually talking about this switch, at the inputs the packets are coming in slots, they are not coming arbitrarily, but the queue will start behaving in that fashion when n becomes very large, okay. So as if I am actually having that kind of queue. So this is because of this Markovian thing. Deterministic means is a constant thing, you know the value, there is single server, and buffer is infinite capacity, buffer never gets overflowed, okay, that is what it means. So this will actually behave as if it is a MD1 infinity queue. We would also like to know what will be the waiting time, okay. So what will be the waiting time of an output queued system? So this waiting time of a packet will consist of two parts. So first part is there will be, when the packet will be arriving, it will be arriving in batch of I packets. So your packet which you are trying to, you will tag some packet and trying to find out what is delay. It is coming in arrival in a batch of I size, but before the batch arrival there are already packets which are present. So these packets anyway have to go out. So delay because of this, I will call this delay as W1, and there is a delay because now this the tagged packet which you have can be placed here, can be placed here, can be placed here, equally likely it can be placed anywhere. There is no order, there is no preference between all the packets which are being pushed out to the outgoing port, okay, because it is an output queued switch. So depending on where it is being placed, I call it W2. So total delay W will be now given as W1 plus W2. So what we need to find out is the statistics. So we will be using, if I take the Z transform or generating function for this delay times, I can always write at W1Z into W2Z. This again is a standard result from probability theory, and I am actually using that, okay. So using this we need to find out what is W1, what is W2, and then make an estimate of what is going to be my delay in the system, okay. So we stop now, and we will in the next video we will be looking into how the delay will be estimated in the system.